Let's take a look at what are the material properties that we considered when we are looking at thermal properties. Melting point, minimum service temperature, maximum service temperature, glass transition temperature. These are some options. The conductivity, the specific heat, the CTE, thermal shock resistance, especially for ceramics. You cool something too fast, then what happens? These are some things to be considered. It will be useful while reviewing chapter 3 to look at the definitions of these materials, the units, and how they get put to use, in addition to seeing what are typical ranges of properties. Another thing we looked at, especially moving from constraints to objectives, was make something cheap as possible or make something light as possible, right? Density and price become important. In addition, usually in mechanical engineering design, you would have to focus on mechanical properties, modulus, yield strength, ultimate tensile strength, compressive strength, failure strength, hardness, elongation, fracture toughness, material toughness, other things like damping, so loss coefficient, and fatigue properties. Good to refresh, especially this lower category of material properties, because you don't come across it very often in your earlier courses. In addition to mechanical properties, you have to deal with a range of optical properties. In addition, environmental properties, so the whole green revolution and the green economy offers many opportunities for new product design and new products to be released to market. And so in order to take good advantage of that, being able to look at designing from an environmental performance is very important. In addition to environmental impact, environmental resistance is really important for most applications. Does it oxidize? Does it corrode? How quickly does it wear? And so being able to go through these options. If you go into healthcare and product design for healthcare, is it toxic? Does it react? Does it degrade? Is it degrade fast enough? Is it biocompatible? These are all aspects of interaction with the environment which are dominated by surface and interface properties as opposed to bulk properties, something to pay attention to also when we look at material properties. So far, we have looked at bulk and surface properties of the materials used to make components. You have to also look at properties of the materials that enable shapes to be created. Okay. So for instance, in a casting related process, sand casting, die casting, investment casting, injection molding, slip casting, tape casting, for the range of materials, go to look at the fluidity of the material to be able to be translated into a shape. So viscosity is one type of a fluid property, defined by this term Atre. So the stress is proportional to, in this case, the shear rate, which is the equivalent of strain rate for solids, and the constant of proportionality is viscosity. So it's defined. The shear stress is defined by tau, and shear rate is defined by this gamma dot. And compared to tensile or compressive strength for a solid, this is a shear strength that we, and shear stress, that shear deformation that we are interested in for fluids. The coefficient of viscosity has units of Pascal seconds. For Newtonian fluids, the viscosity is a constant. That is, the shear stress does not change as the shear rate is changed. Okay, so this viscosity is a constant of proportionality. So the shear stress changes as a function of shear rate, but the viscosity as a constant of proportionality is a constant. That's Newton's law. When a fluid does not obey this Newton's law, then you have a non-Newtonian fluid. And in this case, the shear rate as it changes, viscosity can change. Usually at very low shear rates, the viscosity is Newtonian. The fluid behaves in a Newtonian manner, viscosity is a constant. And sometimes, as you increase the shear rate, depending upon the fluid, the viscosity can reduce, and so that makes it non-Newtonian. Certain kinds of fluids, the viscosity can increase as well. Okay. So you can see for polymers, they tend to be non-Newtonian, especially in the processing range, in this case, the injection molding range. Let's take a look at what this means, right? So you have a flow through a cylindrical channel, let's say. Right? So the shear stresses depends upon the pressure drop, it depends upon the radius of the channel, it depends upon the length, right? So you have pressure drop per unit length. The shear rate in this channel through in fluid mechanics classes, if you recollect, is proportional to the volumetric flow rate and inversely proportional to the radius of this cylinder. So 4Q by pi r cubed, where P is the pressure, the Q is the volumetric flow rate, and R is the radius of the channel. If you put all these things together and you rearrange terms, you basically have viscosity, being a coefficient of proportionality between tau and gamma dot. And if you rearrange these terms, you will get a way to be able to measure viscosity for a given flow situation, depending upon the pressure drop, depending upon the geometry of the cylinder and the flow rate. Okay. Let's see how to put this into an example.